Hello everyone, I'm Xguo. Today I will present to you our recent work on improving sound absorption through nonlinear active electroacoustic resonators. The electroacoustic resonators refers to the electrodynamic loudspeakers used as membrane-deep resonators. They have a variety of applications in acoustics and in other related fields. One main domain of their application is for constituting the acoustic liner for favoring the sound absorption or aircraft noise reduction. And they also can be used in the construction of other acoustic devices for achieving specific non-trivial wave phenomena, such as for achieving an invisible acoustic sensor or for enabling the constant pressure propagation regardless the presence of disorder. In the low frequency range and under weak excitation, the electroacoustic resonators can be described analytically by a linear model, as illustrated here by a circuit analogy for the case of loudspeaker closed in the cavity. In this case, the motion equation of the loudspeaker diaphragm can be derived directly from the second Newton law. And in the low frequency range, the pressure in cavity can be assumed to be proportional to the displacement of the loudspeaker diaphragm. Therefore, it is possible to rewrite this motion equation as a function of the diaphragm displacement, the pressure in front of the loudspeaker, and the electric current. The active control approach that we proposed is based on the assignment of this current. More specifically, for a loudspeaker closed in a cavity, we take a detectable acoustic quantity as the input to the control system. And then in the control system, we define a transfer law which allows the transfer from the detectable acoustic quantity to the output current that will be sent back to the loudspeaker. In our laboratory, we have already developed a linear impedance control approach, which is based on the measurement of the pressure in front of the loudspeaker. So with this front pressure as the input to the control system, the feedback current can be assigned through the definition of the transfer function in the control system. In the frequency domain, this transfer function can be derived as a function of the target impedance, ZST, and the impedance for the open circuit case, ZAS. For the regarding the control law for the presented study, we will consider only the 1 degree freedom law to assign the target impedance, in which we have 3 assignment parameters. They are mu1, RST, and mu2. This parameter will be used to adjust the impedance property of the active resonators. And now, how to achieve a nonlinear control. Reminding that in the low frequency range, we have a linear relation between the pressure in cavity and the displacement of loudspeaker diaphragm. So we can take this pressure in cavity as the input to the control system. And then it is possible to define a nonlinear stiffness with a cubic nonlinearity on displacement through the definition of a nonlinear transfer law, which allows the transfer from the pressure in cavity to its cubic product. And additionally, we will add a nonlinear parameter beta, which allows to assign the nonlinearity of the achieved active resonators. And in addition to this pure nonlinear control, we consider also to combine the linear control with the nonlinear control to define what we call the hybrid control approach. In this approach, we consider both the pressure in front of the loudspeaker and the pressure in cavity as the 2 inputs to the control system. And then in the control system, we define separately a linear transfer law and another nonlinear transfer law. The 2 resulting current will be summed to produce the final feedback current, which will be sent back to the loudspeaker. In the presented study, we are interested in the sound absorption performance of the acoustic resonators. We know that for a linear system, the absorption coefficient can be defined directly as a function of the acoustic impedance. But for a nonlinear system in which higher harmonic will be generated, such definition is no longer valid. So for the studied nonlinear problem, we propose a more generalized definition of absorption coefficient, which is defined as a function of the reflection coefficient of all generated harmonic. To determine such defined absorption coefficient, we need first to derive the reflected amplitude of all generated harmonic, and then we also need to estimate the amplitude of incident wave for the whole frequency range of interest. To this end, the measurement will be carried out in time domain by considering a stepwise sign excitation. With such linear source, all the nonlinear components will present only in the reflected wave. Thus, it is possible to extract the reflected amplitude of higher harmonic directly from the measurement of total pressure amplitude. And regarding the incident wave, its amplitude becomes accessible if we can achieve an anechoic determination. For this, we consider the aforementioned linear impedance control, and in the corresponding control laws, we set the target resistance to be equal to the specific acoustic impedance of the air. And we show in the figure below here, by the red point, the perfect absorption achieved for each segmented frequency range. So by summing all these results of perfect absorption, we can have finally the amplitude of the incident wave for the whole frequency range of interest. This will be used to derive the absorption coefficient. And in the presented study, the excitation amplitude is fixed as weak as around 1 Pascal. So as a result, the nonlinear effect will be only triggered by the control system. So here we show for the pure nonlinear control case, the process to derive the absorption coefficients. Based on the time domain measurements of the pressure and velocity, we show in the first column the Fourier transform of the measured pressure and velocity at each excitation frequency. From this frequency response, we can extract the amplitude of all the components, which means of the fundamental wave and also of the higher harmonics. In the second column, we show the extracted amplitude for the second and third harmonic. And then following the definition of the proposed definition of absorption coefficient, we can derive with measurements the absorption curves, which for the achieved nonlinear resonators, which takes into account the generation of higher harmonics. From this first result, we can see that the proposed nonlinear control can change the absorption performance of the achieved active resonators, and the corresponding generated higher harmonic remains very small comparing to the fundamental wave. And then for the considered hybrid control case, we fix always the excitation amplitude at around 1 Pascal. The linear part and the nonlinear part control law will be adjusted through the assignment parameter, so the linear parameter and the nonlinear parameter beta. So here we show for two hybrid control cases by considering the same linear part of control law, but with different setting of nonlinear parameter. From this result, we can see that the proposed nonlinear control approach can improve the absorption performance of the active resonators. And with the increase of the nonlinear parameter, the improvement of the absorption performance becomes more and more noticeable, especially near the resonance of the resonator. And the generated higher harmonic remains always to be negligible comparing to that of the fundamental wave. And then it is also possible to consider different control law to combine with nonlinear control. And we can conclude here that it is always possible to improve the absorption performance by the proposed nonlinear approach. And we can also conclude that the proposed nonlinear control approach provides another possibility to trigger nonlinear effect, not by increasing the excitation amplitude, but by directly adjusting the nonlinear parameter of the control system. Since in the proposed active control approach, any detectable active quantity can be considered as the input to the control system. So we can use two microphones in front of the loudspeaker to measure the pressure and derive the velocity of the displacement, to derive the velocity of the loudspeaker diaphragm. And then in the control system, we can achieve a nonlinear resistance instead of a nonlinear stiffness. Here in this figure, we showed a preliminary result of absorption coefficient, which is achieved by sensing directly the velocity through a vaporometer. And from this result, we can see that a nonlinear resistance presents more advantage in improving sound absorption comparing to nonlinear stiffness. This part of study is what we are currently working on. So if you are interested in the presented work on nonlinear active control, you are invited to see the detail in our published paper. And in our university, there has also similar work on active control, which has been developed in the group of Romain Fleury. So thanks for your attention.